My name is Aviv. As you can see here in this beautiful shirt, I am from team Barnyard, FTC team Barnyard 22993, okay? And in this seminar, I'm going to talk to you about a winning software design process, okay? So I'm one of the two hosts of this TechXChange project, and where just teams share, seminars with each other and teach each other. And so far, we had two seminars, which were pretty interesting, and this is the third one. And I hope we're going to learn something new from it and enjoy it. So, okay. Last year I was the captain of the team, and this year I'm the leader of the programming team, the software team. So yeah, I'm just going to show you. I'm going to cover the exact plan my team used this year in order to build our robot's brain, like its software. So this has 10 steps. This plan has 10 steps, and I'm just going to share them with you. So yeah. A thing to notice about this, an interesting thing to notice about this plan is that the programs for the autonomous and teleop are on the last step. So in all of these steps, we are just going to cover, the preparation for the autonomous and teleop programs. We are not going to write any code for, how the robot actually moves. So that's something interesting. And why is that, you're asking? So the reason we're doing that like that is that the number one reason robots fail is due to a lack foundation, okay? Is a weak foundation due to a lack of planning. So this relates also to mechanics and to software. If the robot doesn't have the right foundation, the strong foundation, it will just not be good. Like teams don't dedicate enough time to planning how the robot will be, and then they are surprised when the robot actually, just doesn't work in the competition on the field. So yeah. A worthy design process, a good one, will just a second, will result in first of all, in speed. Why? Because if you have a better code, a more organized code, you will have fewer bugs and you won't need to spend the whole season debugging the code. You will be able to just flow with it and just create it very smoothly. A second thing you will get is a better teamwork. When you have a good design process, you can divide the tasks better and set clearer expectations for the team, which can result in better teamwork and better more and faster progress. And the last thing is strategy. When you think about the process of a software, you are creating a software whose logic is aligning perfectly with a winning gameplay. You tell the robot only to do things which are necessary and to avoid doing things which are unnecessary. So this way you get a better strategy, of course. Okay, now that you understand the importance of a good design process for the software, let's actually start covering the 10 steps. So the first step one, is going to be defining the requirements for the robot, okay? So what I want you to do in the first week of... Okay. כן, הכל טוב, משה, בסדר. טוב, אוקיי. Just a second. Problem here. Okay. What I want you to do in the first week of the season, when the kickoff is starting in September, is to actually dedicate the whole week, the whole beginning of the season, to strategizing, to understanding what is the strategy of the game, to understand the game. Okay, like I want you to study the game, and by that I mean to firstly study the rules. Okay, in every season we get a very long game manual of like 100 pages, just explaining the rules of the game, how the game is played. And I don't want to sound like the judges in the competitions, but for a software team, it's very crucial to understand these rules for the game, because the more specific we can get on what is this game and what is the strategies for this game, the better we can actually program a software. So first of all, understand the rules. Second of all, you really want to understand the scoring options for this year's game. So what we like to do, my team personally, is in the beginning of the season to just watch the kickoff, the video of the kickoff, and write to ourselves all the scoring options. So for autonomous for this year, it could be scoring a specimen on the high chamber will result in 20 points, doing it in teleop will result in 10 points, a sample in the high basket, 8 points, and etc. Just all of the scoring options, just write it down. It's a pretty easy step, actually. Like this is pretty fine. And the last thing you need to study about the game is the challenges of the game. And each year we have different kinds of challenges, but a basic one is the fact that you are playing 3 robots on one field, 4 robots on one field. You need to consider the fact that your robot might, collide with other robots, might, have conflicts with other robots, and this is just a challenge you need. This is an example for a challenge, Now, what is the software's rule in requirements? Now, the software's rule is what does software need to enable the robot to do? So what is the software required to do is what the software needs to enable. Like, the question you want to ask yourself is what are the software requirements? What is required from the software of the robot? And so an example, this is an example for center stage game for last year. So it could be collect pixels from the ground. Okay, the robot needs to collect pixels. This is a requirement from software. The robot needs to score them on the backdrop. It needs to move quickly through the field. It needs to locate the prop position on the spike mark. It needs to not touch other robots' game pieces. And the last one is a challenge, actually. Like, don't touch other robots' game pieces is a challenge because you need to take it into consideration and think about it, stuff like that. And it's also a part of the rules, though. So conditional logic, okay? We need to understand also in requirements under what condition each thing must happen. So let's look at an example of this. In the sentence stage game, if the prop position is 1, we want to drop the purple pixel in position 1. So this is a conditional requirement. It doesn't always have to happen. You don't always drop the pixel in position 1, but you do so when the prop is there. So this is conditional logic. And then after you set and storageized for a lot of time, okay, you should have a list of all the requirements that the software has for the game. So for autonomous, this could be something like this, even though it's better if it's longer, the longer the list, the better, because it means you understand the requirements better. So just try to aim for as long of a list as possible. And here you can say you have a, park in the backstage, detect improp, all of the requirements for the software for autonomous. So this was step 1, define the requirements of the software. And in step 2, we want to go over the resources of the software. And the goal here is going to be to analyze the robot concept, and I mean mechanically, okay? And define resources. So what we want to do here is to go to mechanics team and ask them if they can explain us the concept of the robot. So you can see a nice visual in here. Just, and if your mechanics team can make a 3D model of the robot for you, for the software team, as early as possible into the season, this can really help because then you can really see with your eyes how the robot is going to look like and imagine it playing on the field. This way you can build a better software and define the resources better. So if you're, this is an example of our robot last year. This is a 3D model of it, but it doesn't have the arm and the claw and all the wheels and the webcam, but it still really can help a software team build the software. Now, this is an example of the hardware resources your robot might have. So an example, this is relates to our last year's robot. So it had 3 odometry wheels, 2 distance sensor on the claw to detect whether a pixel is in the claw or not. It had 2 motors moving the arm. It had 3 servers moving the claw, and it had a webcam. So all of these are hardware resources. But there are also other types of resources which are not less important, and we need to take them into account as well. So the first type of resource is, well, time resources, okay? Now, time is a very valuable resource, and an average FTC season lasts about 5 months. So it means the software team has only 5 months to build the software for the robot, okay? So we need to understand it and really take it into account. Another type of resource is human resources. We want to understand how many people we have in our software team, which are available to program the robot. And then we want to also understand the skills and experiences of each individual in the software team. So as you can see in this example, we have another software team, and here you have Emma, okay, who is very good at autonomous localization. Like, she is the one who can create a very consistent and accurate autonomous trajectory for your robot. So this is a resource, okay? This is a skill resource and a human resource. And then you have Bob, who is a vision processing master. He just, since he's 5 years old, he's got his phone, and he's just obsessed with cameras, and he likes, processing vision, So this is a resources, and we're just going to list it now, and later you'll see how we can actually use it. So the final output for the resources might look something like this. Obviously, this should be a way longer list, but here you can see all the hardware components of the robot. You can see the human resources here, and I also included a mentor. A mentor is a very valuable human resource you must include in here. I also included robot testing access because, like, in order to test things, the software team needs the robot a lot of times, most times. Okay, so if the software doesn't have the robot available to them, if the resource is lacking, then they won't be able to test the robot and make the software. So yeah, it's also a resource you need to take into account. Now, moving on to step 3. Whoa, I spilled water on myself. Just a second. Okay. In step 3, we have requirements and resources mapping. Okay. We actually listed out the requirements of the robot. We listed the resources we have. Now we want to make a map. We want to connect the resources to requirements. So here we have it, resources, which are motors, servos, odometer wheels, sensor, webcams, whatever. We have the requirements from the software. So this is going to be to take the team probe, collect pixels, score, localize the robot, climb, whatever. Then we want to connect them. Okay, so like this. So the formula we like to use for connection like this is in order to X, we Y. Okay, so let's look at a few examples. In order to climb, we move our arm down. So on the right, you can see a picture of our robot from last year climbing. Okay, it's just like in order to meet the requirement of climbing, it uses the resource of the arm. In order to score a pixel, we open our claw. Okay. In order to build the autonomous trajectory, we will dedicate 2 weeks. So this is an example of how you can implement a time resource, okay? And now, after doing that, in order to organize things better in your head, we would like to build a map which connects the requirements to the resources. So here you can just list out all the different resources you have and all the different requirements, and then you can start checking what connects to what. So basically, as you can see here, the resource of the arm is used in order to meet the requirement of climbing, as you said before. The resource of 1 month is used in order to meet the requirement of programming a TeleOp. Okay, so these are just connections, and if you have a really big map like that, you will see later how it can help us. Okay, so this was step 3, and now we're moving on to step number 4. Okay, in step number 4, we're going to talk about action mapping. So we have got the software requirements and the software resources, and now we want to build a software. Okay, but before we do that, what is even a software? Okay, so simply said, software is a set of instructions that control what the robot does. Okay, this is simply what software means. Okay, now we know what the robot is required to do. We have listed out all the things it's required to do, and we made a map, and we know what resources it will do it with, but we don't know how. We don't know what instructions exactly we need to give the robot, which means we can't build the software yet. Okay, we need to figure out what exact instructions we will give our robot first before we actually jump into building the software. And this is where action mapping comes in. Okay, action mapping means taking a big task, okay, and dividing it into many subtasks. So our cute robot in here has a lot of big tasks it needs to do, and we want to take each one of these big tasks and divide it into smaller tasks. So an example of this could be the intake, okay? Intake is a big task, and let's see how we can divide it into small tasks. So in intake, this consists of taking the wrist down. So as you can see, this is the wrist, taking the wrist down, okay? Opening the claw, so this is the claw, opening the claw, collecting a pixel, so boop, collecting, okay, and then moving the wrist up. And this is the process of collecting a pixel. This is like the subtasks of the big task, okay? And why will we do that? We also want to operate the LEDs of the robot. This is also a part of the intake. We want to turn the LEDs purple to let the driver know that the process of intaking pixels is operating. And then when the process is finished, we turn the LEDs green and the driver knows that the process was finished, that it can drive and score the pixels on the backdrop. So the final output you want to have in here is a map like this, where each big task is divided into many small tasks. I want to note here something, okay? In action mapping includes the assigning each of the actions, each of the tasks to a programming team member. So, for example, if we take the people from before, we have Emma, and Emma, because she is so good in creating trajectories, is going to be responsible for autonomous localization. And Bob, who is really good at vision processing and obsessed with cameras, is going to be responsible for making the vision processing for the robot. And that's exactly why we took into account human resources and skills in step 3. So now moving on to step number 5, where we're going to build flowcharts. Now we know the exact instructions we need to give the robot, okay? But I have a question for you. How does this map that we built turn into a fully functioning robot? And the answer is flowcharts, okay? In order to take our robot from just a map and to make it actually move, we are going to build flowcharts. Now, what are flowcharts even? A flowchart is a chart which is a detailed blueprint for your code. So as you can see, a flowchart is a bunch of different shapes which are connected through lines. And let's see an example of it, okay? So in order to process our claw in the TeleOp, we're going to use this small flowchart. In each loop of the flowchart, we're going to check if the op mode is active, meaning if the driver didn't click on stop. If the driver didn't click on stop, then we want to process the claw. We want to check if Y was pressed on the gamepad. So the driver has a gamepad. When he wants to use the claw, he presses Y. If Y was pressed, then we're moving on to the next step. We're going to check if the claw is open. If the claw is open, we want to close it. If the claw is closed, we want to open it. So the flowchart basically does this, and then it repeats the cycle again. So it checks if the op mode is active. If the op mode is active, we're checking if Y is pressed. If Y is pressed, we're checking if claw is open. If claw is not open, we're closing it, and it repeats this process again and again and again and again throughout the whole game until the driver clicks on stop, and then the op mode is not active and the flowchart stops. Now, I want to talk to you about autonomous versus teleop, okay? In teleop, what we're doing is we're taking a driver input and a sensor input, and based on that, we're creating a system output. So let's take a look in there, okay? Here, we took a driver input, which is the Y pressed. This is a driver input because the driver clicked Y. And then we want to check a sensor input in order to know if the claw is open or closed. So based on the sensor input and the driver input, we can determine whether the claw is open or closed, and then we can close/open it. So this is for teleop. Then for autonomous, we can have something like this. We have something like this. We get sensor input, only sensor input, and then we translate the sensor input into system output. So by the way, I just wanted to show you something cool here. The only difference between autonomous operation and teleop operation is that on teleop, you have also driver input and sensor input, but on autonomous, you only have sensor input. So this is what makes the difference here. And now let's see what the final input can look like for the teleop period. So for the teleop period, you're going to have something big and scary like this. Actually, don't. I'm just kidding. It's not really scary. Let's break it down. What's really in here? On the top left corner, you can see this. This is just gamepad keys. Okay. This is a description of what each key on the gamepad does. So as we saw with the claw, when Y is pressed, the claw is operated. So this is just that. Here you can see the chart's key. So basically, as I said, a flowchart contains many different shapes, and each shape is representing something else. One shape might represent an input, the other might represent a condition, another might represent a preparation or a data or whatever else, okay? So we have many different shapes for many different operations. And then the rest is just the logic of the code. So this is a loop that just goes and checks each time if a button was pressed or if the joystick was pressed, and then it just operates the robot based on that. Now, let's take a look at the autonomous, okay? Autonomous is a bit different because on autonomous, we don't have the driver input. And another thing that's different in the autonomous is that in autonomous, we don't go in a loop, okay? We actually go step by step. We actually check, like we first score the first sample, okay, in this year's game. Then we go and collect another sample. Then we score the second sample. Then we collect another sample. Then we score it. Then we park. Then whatever, you know? We act based on predefined actions. We don't act in a loop inside the autonomous, but in the teleop we loop through a predefined set of actions, which is just relate to the gameplay input. So yeah, this is a difference here. Now we finished after of the seminar, and now we're going to talk about the project setup. So our goal here is to get a clean structure for the project. Just want you to remember here something, okay? A clean structure for the project will make the development much more faster because you will be able to do things more smoothly and you won't need to think about it that much later on. So yeah, thinking about it in the beginning is good. Here is the folder division my team like to use, and like we have a robot class, okay? So just a place in a place in our project where we operate the robot. We like to have a folder for all the subsystems of the robot. So there you can have the arm, the claw, the wrist, the lift, whatever that goes in subsystems. Then we have an autonomous programs folder. Like we have a folder for it because autonomous is not is not the same if you are starting a different position of the field. So let's say if I'm red and I'm scoring specimens, I will need a different program than if I'm blue and scoring samples. So that's why we have a folder for that. Then we also have the utilities folder, which is basically a folder where we have a lot of helper things, and you will see it there later. I will talk about it. And then we have a teleop class where we basically operate the teleop. We just make sure the teleop works. And then we have a testing folder. So this is just the division for our project, which we find the most comfortable. And yeah, and this is this step, a very short step. And now we want to move on to step 7, which will be GitHub projects. Now, probably most teams work with GitHub, I guess all of the teams here. So I want to ask a question. How can we make sure that the task we assign gets done? So the answer is we track progress, okay? We just track the task and we see how the progress is going, okay? Now, a way we like to track the progress is with GitHub projects, okay? So if you didn't know, GitHub has an option which is called projects. So there is a tab right here and you can just click it and then you see all of your projects. Now, if you don't have a project for this year's game, you can just click the green button and create one. And then when you go into there, you can see this beautiful screen, okay? Now in here, what you can do is easily keep track of how your tasks is going. So for example, if I have here to do, I have a in progress tab and I have a done tab. So the done are the things we have already covered. So let's say make a flowchart for the teleop, make a requirements resources map, create a basic structure for the project. Okay, these are tasks that we have done. Then we have tasks which are in progress, tasks we are currently doing. Okay, so here we can have tune PID for ARM. Okay, so the programmers will understand what I'm talking about. You have here write a description for what each gamepad button does. So this is what we did in the flowchart for the teleop. And we have another tab we have here is to do, okay, to do. Here we just list all of the tasks we need to do. And basically this one should be the longest because like in the beginning of the season, you can already predict what tasks you are going to have throughout the whole season. So you can have it in here. And yeah, so this was this step. And now moving on to step number 8, which is going to be subsystems and utilities, okay? So congratulations, now we can finally start to write some code. All of the other steps were just some preparation and charts and maps and things which are too complicated. Now we can actually write code, which we programmers love to do because we are nerds. Okay. But before we can program the autonomous and teleop, we first need to create a base for our robot. okay? Before we tell the robot how to move, we need to create the components it's going to move, okay? We need to create in the software the lift, the arm, you know, the utilities before we actually tell them, before we actually use them in the robot. Which means we need to create subsystems, okay? And the subsystems could include, as I said, arm, claw, drivetrain, webcam, wrist, LEDs, okay? And we need to create utilities. And now utilities could include Roadrunner. Roadrunner is just a library for autonomous localization, so it could be included in here. We can have servo/motor modules. We can have tuning classes and properties, okay? These are a bit more complex, but programmers will understand me here. And this is basically where we use the requirements and resources map, okay? We build this map and now we actually can use it because when we create a subsystem, like in claw, for example, okay? We can look at the resources, okay? Here we see we have a claw, and then we can see the requirements and see how we can use this claw in order to fulfill the requirements. So basically, we know what is required from the subsystem of the claw based on this. Now, this, oh, okay, I actually went over this, never mind. Okay. Now let's talk about utilities a bit, okay? What are the utilities? Utilities are general helper classes or folders you have in our code, okay? So an example could be Roadrunner, which is a library that helps us create an autonomous trajectories, okay? This is just an helper class, a helper library, okay? Then we have timing helpers, which we can create, and they can help us measure time, okay? Then you have motor modules, which are basically which is a classes you can create in order to help you do reverse kinematics. Oh, what is that? Now, reverse kinematics is basically a thing we did this season, which allows programmers to just tell, let's take an example, tell the lift to move 40 centimeters up instead of telling the lift move 200 encoders up. And then this basically is better because for a programmer, it's way easier to measure centimeters than encoders. Encoders are basically sensors which give you the how much rotations the motor did. So there in reverse kinematics, we can actually transfer between these units of encoders to units that are actually more familiar to human, which are centimeters. So this is what reverse kinematics does. And this is what we're doing in motor module. Now we're moving on to step number 9. Here we're going to do testing and robot. Okay, in here you can see a confused programmer who is debugging a code a week before a competition, and yes, you can see she is very scared because the code might not work in the competition. And my question is, how can we prevent a programmer from debugging a code so much later on this season? And the answer is with testing, testing, and testing again, okay? Before we are adding any code to the robot, we want to make sure we test it first, okay? So that's why you have a folder fully dedicated just to testing in our project. So before you put any subsystem or utility in the code, you want to make sure it goes through the testing. Now that our subsystems and utilities are working, we can finally add them into our robot, okay? But how do we actually do that? So the answer is we add the subsystems into the robot class, okay? Now let's talk a bit about the robot class, which I talked about later a bit. So in the robot class, earlier, okay, in the robot class, we firstly use all the different subsystems to create the actions which are required from the robot, okay? Then we track the robot state. So if, for example, the robot is currently in the process of intaking, we want to make sure we track it and we do it inside of robot class. And then we finally want to create automations for the robot. So automations are basically actions the robot does automatically in the teleop period without a driver interference. So it could be climb, it could be intake. This is just automations, and we want to create them inside of the robot class. This is where we use the action map, which we built, okay? Here, we actually, when we create the robot class, we want to know what actions are required from the robot. And in order to do that, we look at the map and we just see the instructions that are needed for each big task, okay? We look at the subtasks for each big task, and this way we can code the things more easily. Now we're in the final step of this process, and this final step is going to be actually building the autonomous and teleop progress. So finally, after all of the hard work and dedication we've put into preparing, we can easily build our autonomous and teleop programs. Now, all you need to do is just take the flowcharts we built in step 5 and translate them into a code inside of Java, okay? So this is basically the job of a programmer, you know, he's just translating real words, like words in English, into a code which a computer can understand, okay? So this is where you need a programmer, actually. And if you followed all of these 10 steps correctly, you should have a fully functioning software like this. So this is our last year's autonomous, which was pretty good. And you can just see it. Here is this going on the backdrop, and boom. So if you did all of the steps correctly, you should get this. And yeah, that was it. I hope you liked this seminar. Yeah, if you want to find us, we are on Instagram, YouTube, Gmail, probably also in other places. Uh, Anybody has any questions? Okay.
No, but I want to say thank you very much for the lecture.
Oh, quite. Thank you for listening.
Aviv, that was a great lecture and I've learned a lot. Thank you.
Oh, thank you, Yoni. We love you.
Oh,
Okay, so guys, thank you all for joining in today. I hope you learned.
Thank you very much.
Have a great day. And
Thanks.
tomorrow, Everglow will present a seminar about SparkFun, which is an odometry sensor. Okay.
Odometry tracking, optical tracking odometry sensor.
Yeah. So it will happen in 3 p.m. and we will like to see you all in there. So yeah, goodbye, everybody.